In this section, we're going to take a look at the radius of convergence and the interval of convergence for a power series. And the first thing we need to do is we need to define what is the interval and radius of convergence. So we're looking at power series, and we recall that a power series is essentially a polynomial. And it looks like this, the series from n equals 0 to infinity, c sub n, where c sub n is some arbitrary coefficient, x minus a to the n, and it's centered about a. And essentially, we just substitute 0, 1, 2, 3, 4, 5, etc. back in. And remember in the previous video series that we use power series to be able to evaluate not so nice sort of expressions and values, something like the cosine of -1/2, or something like e to the 0.10. All right, so that's the whole use of our power series. We can use them to model transcendental functions. Now, the question is, on what set of values is this power series convergent? And that's what we're going to be looking at. Okay, so the interval of convergence essentially answers the question, where is the series convergent? All right, so for what set of values? And then the radius of convergence is going to be the distance from the center of wherever the function centered about. All right, so we're going to find two things for each of these. We're going to find the radius and the interval of convergence for each of these. So now what we're going to be doing is we're going to be using the ratio test and the root test for each of these. So, so let's see some examples to where we can determine where these sorts of functions or these sorts of power series are going to be converged upon. So the first one we have a really basic series, n equals 0 to infinity, 3x to the n. All right, so that's our power series. So here's what we're going to do. We're either going to use the ratio or the root test first. Now, in this example, we're going to use the root test, and we can use the root test if everything is raised to the power of the index. Okay, so if all terms are raised to the power of the index, right? That's when we can use the root test. If anything's not raised to that power, the ratio test is going to be better, or we have factorials. Now, we recall that the root test suggests that if we take the limit as n approaches infinity of the nth root of a sub n's absolute value, and that equals L, and L is less than 1, then we have a convergent series. All right, so that's what we're going to use. Is we're going to use this property right here to be able to determine if we have a convergent or divergent series. All right, so let's keep that in mind. And what we're going to do is we're just going to apply that rule. All right, so let me refresh this a couple times just so I can get rid of some of the stuff. And what we're going to do is we're going to take the limit as n approaches infinity of the nth root of the absolute value of 3x to the n. And that has to be less than 1, right, for us to be able to get to some sort of value. Okay, so what we're going to do is we're going to cancel out the n's, just like we always do. And then we're left with the limit as n approaches infinity of the absolute value of 3x. The good news is that there are no n's in this one. All right, so what we're going to do is we're just going to apply the limit, but there's nothing to apply since the n is going to be sort of this independent, or x is independent of the variable n. And so really, we just get the absolute value of 3x is less than 1. And then if we were to write that as just some sort of regular inequality, we would get that -1 is less than 3x is less than 1. All right, so that's a compound inequality. That's when this is going to be true. And then if we divided everything by 3, we could get -1/3 less than x less than 1/3. Right. Now, we also have to check the endpoints. Okay, so we want to determine what happens at the endpoints for each of these. Okay, so we are going to check the endpoints. Okay. And what that means is we're going to substitute minus 1/3 for x and positive 1/3 for x. And we're going to do two series tests. All right, so that's the goal after we get this initial interval of convergence. Okay, so this is like the first part to what we do these problems is that this is going to be the initial interval of convergence. So interval without the endpoints. All right, so now let's go ahead and test what happens at the endpoints. Okay, so if x were equal to minus 1/3, okay, the original series we just substitute back in becomes the series n equals 0 to infinity, 3 times minus 1/3 to the nth power. And then if x were equal to positive 1/3, this would be the series n equals 0 to infinity of 3 times 1/3 to the nth power. All right, so all we're doing is we're just substituting the 1/3 back in. And by simplifying this, we literally get the series n equals 0 to infinity of minus 1 to the n. And then we also get the series n equals 0 to infinity of 1 to the n. Right? And what we want to do is we want to determine the convergence or divergence of each of those series. Now, this one's easy, okay? Because think about this. If you just keep adding up ones, okay, so this series is really going to be 1 plus 1 plus 1 plus 1 plus 1 forever, all right? Notice that the limit of this series never goes to infinity, all right? So this one's an easy one to see that it diverges, all right? However, this one is an alternating series, all right? And if we wanted to show that it diverges, we could use the alternating series test. So for this one, what we're going to do is we're just going to start by determining whether, so I'm going to call this, remember we take the absolute value of minus 1 to the n, okay, which is going to be equal to 1 to the n, right? And then we just want to determine if the terms are going to be decreasing, okay? But clearly they're not going to be decreasing, okay? So if I had like a small table where n is 0, 1, 2, 3, then a sub n, okay, which I'm going to call this, is going to be 1, 1, 1, 1. But also if I took the limit as n approaches infinity of 1 to the n, okay, well, that's going to be 1 to the infinity, which we don't know what it is, all right? Or essentially, it's just going to be 1, okay, because 1 to any power is going to be 1 anyway, which is not going to be equal to 0, okay? So clearly, by both cases, this part diverges as well. All right, so two things that we can say about this. We know that the interval of convergence is going to be from negative 1/3 to positive 1/3, exclusive of the endpoints. All right. And then the center of this is at 0. Okay. So the radius of convergence is going to be 1/3. All right. And we could see that right here is because if we were to solve this, we could just say that the absolute value of x is going to be less than 1/3. All right, since we can write this, we could write this guy right here as 3 absolute value of x if we really wanted to is less than 1. All right, so the radius of convergence, the distance from the center, is going to be equal to 1/3. All right, a lot of times in mathematics we call that capital R. Okay, so that's how we find the interval and the radius of convergence. And you can clearly see in the middle of this interval, in the middle here is x equals 0. So the distance from each on the number line, if I was to draw a number line for this, that probably would have been a little bit easier for you all to see if I just didn't do something different. But All right, we can clearly see that the distance 0, we have a 1/3 here, and then we have a minus 1/3. All right, and this is our interval of convergence, and the distance r from both of those is called the radius of convergence. Okay, so for this power series, essentially what we're saying is that values like 5, 17, 35, numbers that are outside this interval, it's going to make it diverge. But any numbers that are between negative and positive 1/3, okay, so for instance, 1/10, etc., it's going to make this series converge, okay? And actually, you could see that pretty easily, all right? So let me show you one way to check to make sure that if you were to substitute a number inside of the interval, okay? So remember, we just said that the interval was minus 1/3 to positive 1/3. And we know something like 1/10 falls in here. So let's substitute x equal 1/10. All right, and I'll just show you what happens if we do that. That becomes the series n equals 0 to infinity, 3/10 to the n. And this is a geometric, right? So the geometric series with r equal 3/10, which is less than 1. So that's a convergent series. All right, so however, if I pick something like 10/5, all right, which is outside of that, then we would get a geometric series with r is greater than 1. All right, so just some ways for you guys to be able to check your answers once you're done. Just plug in a number somewhere within that interval of convergence, and you'll see that if you did it correctly, that the series is going to converge. Okay, so that's what the interval of convergence is. That's what the radius of convergence is. All right. So for the rest of this section, we're just going to take a look at various examples where we find both the radius and interval of convergence.